Okie dokie. Now we are up to the equivalence point of our weak acid strong base titration. Now, up until this point, we have had some weak acid and we have been adding strong base to it. But at the equivalence point, like we saw with the volume calculation or the explanation for part E, we have added the same number of moles of base as we had acid initially, or that's 2.5 times 10 to the minus 3. And so as we added that strong base, it reacted completely, and so none of that strong base is present. And it reacted completely with this weak acid. So also, none of that weak acid is present. It also turns out that all of that weak acid happened to get converted to conjugate base. And so now the only thing in solution that can do anything to the pH is this conjugate base, this formate anion, that likes to pick up a proton and form that conjugate acid again. And so what we have when we get to the equilibrium point is this conjugate base acting as a conjugate base, changing the pH and making it slightly basic. And so we need to focus, or switch our focus rather, from this equilibrium with the weak acid to the equilibrium that's formed between this conjugate base and the water molecules that were A, already present, or B, formed from this first equilibrium that we drew. Now, conjugate bases will act as bases, and so we're going to make an OH minus, which implies that we need a KB, and then once we use that KB, it implies that we're probably looking at POH instead of pH. So as we move forward, we got to keep these things in mind because we'll probably have a little bit of extra work. Now again, we've used up all of the weak acid. There's no strong base left, and we're left with nothing but conjugate base. And so what's in solution is really just a simple ice table. And this is in terms of moles, not volume. So I'm going to have to divide by the total volume. We have 25 milliliters of acid. The last question asked you to get the volume of base that you needed to add, which happened to be 16.7 milliliters of base. And so you're going to end up with 41.7 milliliters total, everything that's in the flask. Now, we can't have that as milliliters. We have to have it as liters, but it's a quick conversion. Okay, so I'm going to do that math. That math will give me a molarity. Initially, there were none of either of those ions. So I have to add concentration to that side. I'm going to have to subtract concentration from the reactant side. And then I'm able to solve for the equilibrium line of my ice table. Now this concentration, this calculation here, ends up giving you a value of 0.06 molar. I'm going to subtract x from that. This is x and that is x. Now, I have a bit of a problem, not a hard problem, but a bit of a problem in that I'm given the Ka for formic acid, and I don't need a Ka. I have a conjugate base forming hydroxide ions as it acts as a base, and so a Ka is inappropriate. I need to make sure that I have a Kb. But Kb is just going to be Kw divided by Ka, so another relatively quick conversion. And I get a value of 5.56 times 10 to the minus 11. So now I have something that I can use. Not a difficult step, but I do have to remember it. So I'm going to set up my K expression. I'm going to set it equal to the products over the concentration of the reactants. I'm going to use my 5% rule, and I'm going to drop that x. So we can solve for x, and when we do that, we get the concentration of hydroxide ions. that concentration is equal to 1.83 times 10 to the minus 6 molar. Now you got a couple of options. I like to go to the PaOH first, and so that's what I'm going to do. I'm going to take the negative log of the 1.83 times 10 to the minus 6 molar. And I'm going to remember that that gives me POH. And that number is going to be 5.73. But that's not the pH. That's not what I've been asked to solve. So I'm going to take 14. I'm going to subtract that POH from it. And I'm going to get a value of 8.26 for the pH. Now this is a weak acid, strong base titration. The pH should be greater than 7 because we should have a conjugate base in solution. This weak acid is a little bit stronger than other weak acids we have dealt with. So the fact that this pH is a little bit lower than other calculations we've done, but still higher than 7, looks like we've come up with a pretty reasonable answer.